Okay, well, let's get started. I'm sorry we're running late today. I'm going to go over the exam real quick. I think the grades were pretty good for an exam in this class. I mean, the exam scores tend to be a little lower, but I generally curve at the end. So I'll just quickly go through this. If you have any questions, let me know. Question one, 88% of the class got this right. Basically, if you want to set bit 1 to 1, you want to take a 1 shifted by, set bit 3 to 1 rather. You could take a 1 shifted 3 bits and then OR it into a value. How many wires are needed for a UART channel? It's just 2. That was 88% was correct on that. Question 3, a peripheral is a base I/O address of 100400 with size 1C00. What's the highest byte address? You basically just add. So you take the base address and you add the size. But you'll notice that the size is 1C00. Both the base address and the size are in hex. So you have to subtract 1 from the size though, because they're inclusive. You're counting both ends of the range. So instead of 1C00, I subtracted 1 from that in hex, which is 1 BFF. So when you add those two, you get 101 DFF. This was a CPU as an interrupt handler that requires 40 milliseconds to execute and whose interrupt controller.
Are you sure it's 101 DFF? That's not an option.
Yeah, that's not an option.
I'm sorry, I might have.
Wait.
Well, let me check my math here. So 1 plus F is F. 0 plus F is F. 0 plus F is F. 4 plus B is B, C, D, E.
B is 11, so that's like 15.
F, 15. So that should be an F. Thank you.
And that is an option. Okay.
Yeah. Yeah, when I was making the slide, I had D instead of F. There we go. Sorry.
You're good.
Assume a CPU has an interrupt handler that requires 40 milliseconds to execute and whose interrupt controller is level high triggered with no acknowledge. How long must a peripheral hold the interrupt signal high to cause the CPU to execute 2 consecutive interrupt service routines? So this is this question is a little confusing because one of the problems is it ignores the time it takes for the interrupt to respond, for the CPU to respond to the interrupt, which I have labeled as lambda on here. It's kind of the latency, the interrupt latency time. So I try to show what's happening here. If you have an interrupt service routine that's 40 milliseconds, the interrupt handler will go high, and the idea is that we want to keep it high long enough for it to falsely trigger a second interrupt service routine. So the CPU will think that there's 2 interrupts when in fact there's just 1, right? The idea is that the peripheral is just trying to trigger 1, but it holds it high too long. And so the answer was more than 40 milliseconds. Well, that makes sense because it would have to be high for more than 40 milliseconds because that's how long it takes the CPU to execute the ISR. And then I had less than 80 milliseconds, which is the time it would take to do 2, because if it was more than 80 milliseconds, if it was high for more than 80 milliseconds, and if you assume that the latency is 0, that it triggers instantly, which is not, in reality, it's not realistic, but then you could potentially trigger 3 ISRs. So the answer was more than 40 and less than 80. Technically, I should have had this lambda term, like how the difference between when the interrupt goes high versus where you actually start, where the CPU registers that an interrupt has happened. And in which case it would be more than 40 milliseconds plus 2 lambda, and less than 80 milliseconds plus 2 lambda. But I think in terms of the available options, that one is the one that makes the most sense.
I looked in the book and I was trying to figure this one out, and I got it wrong. But in general, it didn't talk about the situation where you have a level high trigger where the level drops midway through the interrupt on a CPU. Do most CPUs or like peripherals, if they say level high interrupt, we can assume that I don't have to hold it for the whole interrupt handle?
Yeah, if it's level high, it'll hold it for some amount of time. It thinks is long enough.
Okay, so it just
for the CPU. So in other words,
the interrupt interrupt, it stops searching for it.
Yeah, well, the objective is that you're trying to guess lambda. Like the CPU will respond within lambda. So the peripheral, as long as it has it high for at least lambda, then it's going to get attention. The problem is if it vastly overestimates what lambda is, then there's a potential to get 2 interrupts. And the reason this is on here is this is all in response, by the way, to the way Arduinos handle interrupts.
This is real world, yeah.
Most CPUs have the acknowledge that comes back that prevents that from happening. So if the peripheral has an acknowledge, then it will know what lambda is, because after the CPU starts interrupting the ISR,
So it doesn't have to hold the high.
right, it'll drop this when it sees lambda. I'm sorry, when it sees the acknowledge, which will happen after lambda time, the latency of the interrupt. So. Yeah, okay, question 5, assume 2 devices are connected to the same wire using an open drain interface. One device attempts to set the wire's logic value to logic 1 and the other logic 1 as well. What is the resulting value on the wire? With an open drain, you can't really, the way you set a logic 1 output is by doing nothing, right? Because it's got that pull-up resistor that's pulling it up. So if you've got 2 devices and they both want to inject a 1 on the wire, then they just they turn off the pull down transistor. And so if that happens, then it'll still be logic 1, basically. Right. Actually, that's true of a push-pull driver too. I mean, even with a push-pull driver, if you've got 2 devices driving the same wire and they both set to 1, that's fine. That's not technically a conflict. You wouldn't want to set it up that way. I mean, hopefully there would be no potential for conflict, but if they just coincidentally both set to 1, then that's fine, but it leaves open the possibility that they'll try to, one will set high and one will set low, which will be a problem. Okay, what can you infer from the SPI transaction shown below? Well, it's apparently a read because we have some activity on MISO. So MISO is the data that would be coming back to the master. So that implies that it's a read. Normally, if it was a write, MISO doesn't have any usefulness for a write, right? All the bits would come out on MOSI. Is there anything else? Yes. The other thing you can tell is CPOL must be 1 because the clock is shown as 1 before anything happens on the channel, and CFA is apparently 1 because the data is changing. The first time the data changes, the first edge of the data, the first transition, or the first potential transition, because like this is a don't care, this gray area, so the data might not actually change there if the MOSI was low and then the first bit coming out was low, right? But on the timing diagram, it's shown that the data, the MOSI is a don't care, so it could be 1 or 0. But if it is 1, if it happens to be 1 and it's going to transition to 0 as the first bit, that would happen at the same time, on the same initial edge as the clock, right? So CFA is 1. So basically, the way I remember this is that if CFA is 0, the data gets a head start on the clock. Well, in this case, it's not getting a head start because they're both kind of initiating at the same time. So CFA is 1, right? Remember, CFA 0 means data gets a head start on the clock. And CFA 1 is they both change at the same time. All right, what's the apparent average analog voltage of a 3.3 volt PWM signal duty cycle? 60 is just 3.3 times 0.6 is 1.98. Which line of code will complement or flip the bits spanning bit positions 9 down to 7 in the variable val? This one had only 42% of the class got this one right. So this was a challenging one. The idea here is that you take, I mean, there's different ways to do this. But in this case, you're going to take 7, so, sorry, 7, the left 7. The left 7 is the value 7. The right 7 is the number of bits you're shifting it to the left. So it's 7 less than 7, which means you start with 7, and then you move it to the left. So the 7, because that's 3 1 bits, that's going to end up having 1 bits that span bits 7, 8, and 9, right? So that's what I'm showing here. 7, 8, and 9 are turned on. Everything else is 0. Because when you do a left shift, you always shift in zeros. So all these zeros here were just injected.
So can you tell the difference of the AND statement and the exponents?
This thing, the caret? Yeah, that is a bitwise. That's a bitwise XOR, the caret. And that's not, I don't know if I explicitly talked about that, but that's something I assumed that you guys had learned in programming. That's a Java, C, Python standard operator. It's an XOR. It flips an XOR. If you XOR a bit with 1, it'll flip the value you get is the complement of the input value, right? So an XOR of 1 flips a bit. So if it's 0 XOR with 1, it becomes 1. If it's 1 XOR with 1, it becomes 0. So by aligning these 3 bits, these 3 1 bits, under bits 9 down to 7, and then doing the XOR, it's going to flip. If this is the input, and then this is kind of a temporary variable, it's going to flip these 3 bit positions with 1, 0, 1. Okay, and then the other bits, if you XOR with 0, it has no effect. So XORing with 0 does nothing. XORing with 1 flips. It flips the bits. So basically, this just maneuvers the 1, 1, 1 into position here under these 3 bits, and then it'll end up flipping those 3 bits and leaving the other bits alone. So these other bits 6 down to 0 from the original input, they don't change. Bits 9 down to 7, they get flipped. That's the, yeah, that one, I was trying to come up with something a little unique, because obviously you can zero them out if you AND with zeros, right? And for the bit field, you know, if you put zeros here and then AND, it'll zero them out. If you put ones here and you OR, it sets them to 1, right? But I was trying to come up with something else we can do. In this case, I just flipped them, or asked, you know, how do you flip them? Okay, this one, what byte value is sent to the master in the second exchange? This one is kind of obnoxious because it's really hard to figure out where the bit delineations are, slots. That's the problem. So there's a couple ways you could approach this. You almost have to start from the beginning and put lines. In this case, let's see, CFA is going to be a 1 because the clock and the data are lined up here. So the data is going to be read starting with the second edge of clock. So what that means is it's actually these dotted lines that are already on the timing diagram, these vertical dotted lines, that's actually where you're going to read the bits, starting with the second one, not the first one. But starting with the second one is where you're going to read the bits. So sent to the master, so that would be MISO, and that's in the second exchange. So we have to start with this second vertical dotted line and count 8 because we want to go to the second exchange. So 1, 2, 3, 4, 5, 6, 7, 8. Oh, actually 9. It would be the 9th, actually, because the 8 covers the first exchange. So we have to go to the 9th. And then once we get to the 9th, you can read the MISO value, that's master in, slave out, starting from the 9th vertical line here. And so that's 1, 0, 1, 1, 0, 0, 0, 0, which is going to be, that's going to be B0, right, B0 in hex. So I think that's probably the easiest way to do it, is start all the way from the left. It's kind of difficult to just look at the second half and try to figure out because like if you do that, you don't really know, if you don't start from the beginning and look at the timing from the beginning, you don't really know if this bit belongs to the first or the second. I mean, obviously there's a 1 here, right, because there's a pulse. But is that the last bit of the first transaction or the first bit of the second last bit of the first exchange, or the first bit of the second exchange, right? I use the whole thing is the transaction, but the exchanges are the groups of 8 bits, 8 cycles within the transaction. Okay, assume there's 5 devices attached. I was surprised, this one, 82%. I actually was worried that this would be a bad one because it's basically a circuits question, and you guys haven't had circuits probably or maybe you're in, Maybe maybe it hasn't been that long because this is supposed to be a junior level class, and you take circuits sophomore year. But anyway, yeah, it's a so this is just basically a circuits question, and so the idea is that what is the equivalent resistance between VDD, which is this triangle, and ground, which is this little T, upside down T thing, right? And so this ends up becoming the 10K resistor is in series with the equivalent resistance of 1, 2, 3, 4, 5, 6 resistors in parallel. And so that's going to be 10K plus, and then to figure out the equivalent resistance of parallel resistors, it's going to be 1 divided by, and then here I've got 5 over 10 mega ohms because there's, it would be 1, it's basically, I've simplified this, it's doing 1 over 1 mega ohm plus 1 over 10 mega ohms 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 plus 1 over 10 mega ohms. So this is 5 over 10 mega ohms, and then there's an additional one here, a 1 mega ohm, which is the load. So these 10 mega ohm resistances is the off resistance of the transistors. So the transistors are turned off, so they're equivalent then, as an off transistor, they're equivalent to 10 mega ohms of resistance between their source and drain, but then the load is only 1 mega ohm. The load, by the way, is the input resistance of the circuit you're driving, of the whatever the input, the gates are, of this, because this is creating essentially the output, but this part is the input. But anyway, it comes out to be, if you work out the math, it comes out to be 677 kilo ohms. Okay, of the protocols, which is not a synchronous serial protocol, 100%. Everyone got this one right. UART. Device connected to a UART channel with even parity receives a value 4-1, including the parity bit. Okay, this one, I had a question. Someone asked about this question, and they argued that this was not very clearly written. So the idea here, so the reason I worded it this way was because the parity bit is meant to be considered along with the data bits as one group of bits, right? So you've got the data bits and the parity bit together are supposed to have an even number or an odd number of 1 bits, depending on if it's even or odd parity. So 4-1 is the total, the payload of the data plus the parity. Now, I think the reason it's confusing is that UART is usually 8 bits per data. And this looks like it's an 8-bit number because it's 2 hex digits, right? But I was kind of abstracting that out because, number one, you can do 7 bits in UART is allowed. So you could have a 7 data bit plus 1 parity. Or this could actually be a 9-bit value, but the 9 bits could still be written as 4-1 in hex if you have leading zeros, one leading zero that you take out, right? So anyway, the point is that 4-1, there's 2 1 bits in the value 4-1, and if you have even parity, that means that you're not detecting any errors, right? Doesn't mean there's no errors, because you could have 2 bits that get flipped, and you could fool the error detection mechanism, but it looks like there's no errors here.
I thought it was the number of bits and the parity thing included in that.
It is, yeah, that's what I'm saying. 4-1 is the data bits including the parity.
So 4-1 has 2 1s in it, right? And then
4 is just 1-1. Unless I screwed that up. Yeah, 4 is 1 0 0 in binary.
But then also the 1.
Yeah, and that's the second one, right?
And then you also get the parity bit.
Well, no, I'm including the parity bit.
Parity
So
bit's included.
Oh,
yeah.
in there.
Yeah, that was what.
Okay.
That was that was the confusing part.
50-50 chance. Oh look, 52%.
Yeah, half the class got it right. So here's so there's the 4-1, and then there's 2 1 bits, and so the idea is that this one would be the parity based on its order because it's the rightmost, it's the least significant bit, so that would be the parity bit, and then the data bits would be 1 0 0 0 0 0 0, which you could either say, well, that's, how many bits is that? That's actually 6 bits there, right? The way I'm showing it is actually 6 bits, but it could be a 7-bit or an 8-bit data with the leading ones being ignored, or leading zeros being ignored. I'm sorry, leading zeros being ignored. Assume an SPI channel has CFA equals 0 and CPOL equals 1. What's happening during the second clock edge? This is 30%. This one was the hardest question, I think. So what's happening during the second clock edge during the first exchange? So this is if this is CPOL is 1 and CFA is 0, the second clock edge would be here. So what's happening there? Second clock edge, well, that's a rising clock edge, right? It would be rising. And if you look at this rising clock edge, the data is changing, right? This rising clock edge, the data is not actually changing, but that's only because the first two bits are 1, 1, right? If the first bit was 1, 0 or 0, 1, then you would have the data changing at the same time as that clock edge. Yes?
So I put that answer on the exam and it was marked wrong.
You went back and corrected.
Yeah. There was someone right after the exam early last week, somebody brought this one to my attention, and the exam had a bug in it in terms of which answer was marked internally in Moodle as being the right answer. So I changed it, I fixed it, and then I told it to regrade. So if you go back and look now, it should be corrected. Okay, of the protocols we studied in class, which uses open drain drivers? I2C, 94% of the class got that right. Suppose a UART channel has a baud rate of 9600, has 8 parity bits, 8 data bits, 1 parity bit, and 2 stop bits. What's the maximum throughput? So that would be 8 data bits divided by 8 plus 1 for the parity bit, plus 2 for the stop bits, plus 1 for the start bit. So it would be 8 over 12, right? Mm-hmm. Yeah, 8 over 12, right? And then that would be the ratio you'd multiply by the baud rate, which is 9600. But the 9600 is bits per second, so then you have to divide the whole thing by 8 to get 800 bytes per second. Right, consider the I2C transaction below. What portion of the transaction was acknowledged? Okay, this one it's a little bit easier to find where the bit slots are because it's level sensitive. But you basically just have to count 9 bit slots, 9 bit periods, 9 times where the clock is high. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's the first acknowledge, and then the second acknowledge is going to be another 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first acknowledge, it looks good because acknowledge is active low. So yeah, so the data was low during the 9th bit, and it was high during the 18th bit. And so it was actually the second acknowledge that was NAC'd or not acknowledged. Which side of an I2C channel has control of SDA during the time in which the SCL signal is high for the 9th time? Well, the 9th time is the acknowledge. So it's the acknowledge, and it's always the slave side because the slave always has to acknowledge the header byte. In JTAG, what state is entered for the following sequence on TMS? 1, 1, 1, 1, 1, 0, 1, 1, 0. So the first 5 ones are intended to get you back to the test logic reset, regardless of where you, because notice I didn't say where you started from. You don't know what state you're starting from, but it doesn't matter because you could be in any one of these states, but if you get 5 ones, you will return to this initial state, the start state, test logic reset. That's just because, like, say, for example, if I'm here, I'll go 1 gets me to here, 1 gets me to here, 1 gets me to here, and then 1 gets me back, right? So no matter where you start from, 5 ones will get you back. And then once you get back, additional ones will keep you there, right? And then, so then all you have to worry about then is the 0, 1, 1, 0. So that gets you 0, brings you here, 1 gets you here, 1 gets you here, and then 0 gets you there. So capture IR. So you just have to follow the edges. So capture IR, yeah. Of the protocols we studied in class, which offers error detection, that's UART. That's weird that that one was low, 48%. Error detection, maybe it was the term, the wording. And then suppose an SPI bus has 5 attached slaves with 1 SS signal. How many cycles are needed for the master to exchange 8 bits with all 5 slaves? Basically just 8 times 40 cycles. And 1 SS signal implies that it's a round robin. It's a daisy chain setup. Yes?
For the error detection one, I saw I2C and put that one because I considered like the acknowledged to be.
Oh. Yeah, that's a good point. Is the acknowledged considered an error detection?
Forget, does I2C have like, I know it has acts, but does it say like this is an even parity or an odd parity?
No.
Standard?
No, it doesn't have
You have
that.
no idea whether or not it's right or wrong.
The ACK is designed to make sure that someone's listening to you,
Yeah.
that the other side received the message you're sending. And so there's an acknowledgement for the header byte, an acknowledgement for the data. So if there was an error, the other side would probably still just read the errored bit and still acknowledge. Because there's no way to know that there's when I meant error detection, I should have been more specific and said data error or data bit flip, or I should have been more specific about the type of error. Like one type of error is like someone just comes and cuts the wire, in which case the acknowledgement would catch that, right? Because there would be no acknowledgement. But if there was noise on the channel that caused the bit to flip, then there's no acknowledgement for that in I2C. It's not robust for that. So that's what I meant. But yeah, I mean that's a fair argument though.
I was also thinking like if the slave was unresponsive at any point in time, it would also catch that.
Yeah, if it locked up or hung or malfunctioned or powered down or something, yeah, it would detect. Yeah, it's not. Yeah, I really meant a channel error, but you're right. I should have been more specific. I can go in and mark I2C as a correct answer and regrade for that as well.
I can see that.
Because that's a 4. Because I'm actually surprised that must have been what caught everyone up because of the low grade on that one. Okay, so I guess we're good. All right, so moving ahead. Let's see, where are we in the class? So we had spring break last week. Lab 2 was due on Monday of spring break, but it's technically wouldn't be late if you submitted it
Sunday.
Yeah, Sunday, yeah, because of the school day thing.
We should say lab 3
What's that?
on this bottom one instead of lab 2.
Oh, yeah, sorry, that should be lab 3. That's a typo. Yeah, sorry. Lab 3 is out. I posted it there. And we have quiz 5 also is available. And I need to access these slides because for whatever reason they didn't make it into the repo.
Catch me in the lab tonight doing lab 2.
Okay. Make sure you demo lab 2 because you have to. We base the late penalty on when you submitted it, but you have to demo it to receive a grade. Okay. So the last thing we talked about in class was SystemVerilog, and I'm kind of conflicted about this because I'm not intending for this to be a thorough treatment of SystemVerilog. I just want to give you an introduction to it, a taste, just enough to get something working on the FPGA. In 6.11, we cover this much more thoroughly. The reason I bring it up, though, just so you know, if for those of you that have ever used MATLAB or Simulink, so whenever you design a control system, a real-time controller using Simulink, they want you to generate HDL. Because HDL is deterministic. It always runs in the same number of cycles. I mean, unless there's some kind of a conditional behavior in there. But if you're designing a controller, like we're gonna cover in the next section of this class, when I say controller, I mean like a controller, something that controls a plant, or robot or whatever. It's generally preferred to have a SystemVerilog for that because you don't have to worry about timing uncertainty from interrupts and cache misses and page faults and stuff like that, which you get with a CPU. Now there are real-time CPUs. In fact, ARM has a whole line of CPUs called the ARM Cortex-R chips, and those are real-time. But they're only real-time because they don't run an operating system. They run in bare metal like an Arduino. In fact, Arduinos are basically a real-time operating system, they're real-time. They're a real-time system because they don't have an operating system. You don't have to worry about the operating system interrupting and taking control of the CPU. But there's still the potential for example, interrupts even on Arduino. Like the interrupt service routine that we talked about could interrupt a controller and cause it to take longer to execute than you want. So anyway, that's the reason I bring it up. Is it's because of the theme of control in cyber-physical systems. So I think we got through most of the slides here. We talked about Verilog modules. We talked about numbers, the always statement. We talked about sequential logic and operators, bit manipulation. We talked about blocking versus non-blocking assignment. And I think this is where we left off. So we're using SystemVerilog because that's the latest version of Verilog. It's also the textbook that I use in 611 forced me to upgrade from Verilog to SystemVerilog. The way I teach it, though, I mostly just cover the part of SystemVerilog that also works in Verilog. But there is one notable difference, and I need to bring this up because this is a limitation of Quartus. When you design an IP block in Quartus, they force you to use Verilog and not SystemVerilog. So the one difference that can be annoying is that in SystemVerilog, we declare everything as a logic. All the signals are declared as logic. Now, there's other data types, but we use logic because that's the one that's intended to be synthesized into a wire, into a physical wire, right? In Verilog, there's actually two types that you use instead of logic. There's wire and reg. And the difference is that reg is used whenever you're declaring something that's set in an always statement. And wire is used for everything else. That's the only difference. Now, the question I have is why? Why do they make that distinction? I don't know. It's really obnoxious because it's very easy to forget that, or to declare something as a wire and then you drive it in always statement and then you get an error when you try to compile it. So just be aware of that. It's just kind of an annoyance. It's something they fixed in SystemVerilog with this logic type.
I think that there's some like basic checking built in before it simulates it for register. You can't like assign a register with no state.
Yeah.
Check for that. But the difference between wire and logic, every time I Google it, I'm like.
But reg doesn't actually mean register, though. That's the crazy thing, because you could design combinational logic in an always block that's purely combinational, like just a lookup table, but you still have to declare it as a reg. So that's what's, to me, is confusing.
I think you also accidentally build latches out of reg as well.
Oh yeah. You could. Yeah, that's just. That depends on how you define the always statement.
It does the state thing.
Now, one other thing I want to mention, because this is going to be required for it's not required for the lab, but it'll simplify things for you when you do the lab 3, is this generate statement. The generate statement, I think I mentioned this in the last lecture, it's a for loop that gets unrolled, and it's a way to have the compiler statically copy and paste code a bunch of times, right? It's useful for when you build arithmetic circuits, like if you want to take some adders and connect them together to make a bigger adder, right? Or you want to take adders and array them to make a multiplier, or if you want to build a memory, some kind of a memory with multiple banks. The generate statement is just a way to copy and paste code. So the syntax is so weird, though, that I can never remember this. I always have to go back and refer to this example whenever I write a generate statement, because it's just so weird, the syntax, I can never remember it. You start out by declaring a genvar I, which is just the loop iterator variable, and then you say generate. Now, do you have to have this genvar immediately before the generate? I don't think so. I think as long as you put it above it. That usually they're right next to each other, though. Usually, right? But you have to declare I. And then you say generate for I equals 0, I less than whatever. In this case, I used n because n is a parameter. And so by changing that parameter, I can then define how much I generate inside this generate loop. And then I equals I plus 1. I plus plus doesn't work. You have to use I equals I plus 1. And then begin, and then colon. This is the part I always forget. This is the colon. Colon, and then the name, gen name. This could be any identifier. And then you can put code. And then after your code, you put end and end generate, which seems redundant. Because the end ends the for, and the end generate ends the generate. But you might say, wait a minute, the generate and the for is, that's one statement. They're together, right? Generate for, but yet generate for is one statement, but yet you need an end and an end generate. So even though you began this with one line, you have to end it with 2 lines. I don't know why. Okay, so the code that's inside the generate, though, can be whatever you want. Anything you want to replicate. It can be always statements. It can be structural code. It can be assign statements. Anything you want. In this case, I just have structural code, and I'm creating an adder inside the generate, and then the adder just keeps getting copied and pasted n times. Now you might say, wait a minute though, how do you you're copying and pasting, but what differentiates one from the next? It has to do with the I. I is used when you do calculations for the bit widths, the bits ranges, right? So notice that my adder, I'm basically generating adders, small adders to create a big adder. And so I have this thing called big A. Big A is 32 bits. But these adders are only 8 bits. So I have to generate 4 of these adders together. And I have to connect up their carries together, right? But the A input, which is 8 bits, is going to get an 8-bit slice of big A. Which 8-bit slice? 8 times I plus 7 down to 8 times I. So this will start out being 7 down to 0, right? And then 15 down to 8, then 23 down to 16, and then 31 down to 24, right? So basically, that's the only thing you can do, as far as I know. There might be some. As far as I know, the only thing that you can put in this code that differentiates each one of these adders is functions of I in the bit ranges. There might be another way to. There might be you might be able to do an if with that I or something, but I don't.
And if you were to then use my adder, either in the same module or a different module, you would just play with big A and big B.
Yeah, exactly.
It would distribute that.
Yeah, which is what I'm doing. So big A and big B are well, they're declared internally, that was kind of dumb. I probably should have made them inputs, but basically they're declared in here, and I've got big S, which big S is the sum, and then these guys, you would set a 32-bit number in these big A, big B, and it would get broken up into 8-bit chunks and sent into the 4 smaller adders. Now you might say, why are we using this in Lab 3? It's because we want to independently control all 26 LEDs. So as you might imagine, you're going to have a generate with 26 iterations, and you'll put code in here that drives each of the 26 LEDs. That's the reason why. This is kind of an obscure Verilog thing, but it's very useful for the LED stuff in this lab. Okay, great. Do I have time? Hopefully I have time to do a demo. Yes, okay, so let's, I'm going to do a demo here and show you how to add, how you add IP blocks to Platform Designer. So if we go into Linux here, hold on. Here we go. Cool. All right, so I've got a Linux prompt here, and do I have internet access? No, I need to get network access here. EduRoam 3, yeah, it should be on. All right, hold on one second, sorry. SSH-P222 jbakos at L-3D22-01.CSCE.CU. Yeah, we're good. Okay, now the other thing I want to do is I don't want to actually do the synthesis on my laptop because it'll be too slow. So I'm going to show you guys a trick. This might be useful for you if you work on your laptop. There's this thing called SSHFS. Stands for SSH file system. So I've got a, let's see, where are we at here? Oh yeah, sorry, switch that over here. So I'm going to create a directory here called mkdir lab machine. And then I'm going to type SSHFS jbakos at L-3D22-01.csc.sc.edu port 222, and then I'm going to add actually just put a colon after that because I'm just going to say I want it in my home directory. And and dash, yeah, that's it, right? Bad address. Hold on, let's put the P first. Bad address, come on, I just did this morning. Is it no space? Wait, hold on, let me just look at what I typed in before.
It might be like capital P, I guess.
Yeah, it could be. Let me exit.
You're on the lab machine, that's why your history is much shorter.
Okay, let's try that again. No, sorry, I want to get out of tmux. Let me try it again here. History, grep, sshfs. There it is. Okay. Okay. So sshfs, jbacos at l-3d2201.csc.cu, colon, and then dash p222, and I'm going to say lab machine. Transport endpoint is not connected. Did I already do it? No? Oh, okay, that's why. You're right. I must have been on the wrong system. Sorry.
Yeah.
Create a directory lab machine, and then, no, 2. I'm in lab, that's why. I know it's okay. Go back here. Make create a lab machine. A file exists, okay, good. And then I'm going to go ahead and SSH that, yeah. Got it, okay. Then once you do that, it'll ask for your password, and then it'll do a duo.
Demos on the fly are always fun.
And, okay, so now once you do that, I'll have a directory here called lab machine, which is my home directory on the lab. So now I have access to all the files I would in the lab, but they're accessible from my virtual machine, right? So that way, now the reason I did that is because I want to run Quartus in the lab
So you can run.
so I can synthesize it faster, yeah. Yeah, exactly. But I'm actually going to run 2 copies of it because it's if you run Quartus remotely, the UI is kind of sluggish. So I'm going to use a local copy for the UI, but then I'm going to use the lab machine to do the workload of synthesizing it. Okay, so back over here, I'm going to exit out of here and type Quartus. So this should be my local Quartus, and then on this machine, actually that's also my local one. Yeah, I need to have a secondary. There we go. And then I'll go back to the lab machine. jbacos at l-322-01 and dash capital Y. Notice I had this dash capital Y. This is what allows me to run graphical apps remotely. And I got a duo again. And then I can run Quartus there. So now I'm going to have 2 copies of Quartus. This will be a little confusing, but just to make sure I keep them straight. Okay, now I'm going to open up I'm going to open a project on lab machine. So I'm opening a project on the my lab file system, which is going to be lights. Lights. This is the demo that I left off with last lecture. And then I'm going to go to the lab machine Quartus, and I'm going to open the same one on there. See, you see what I mean about it being clunky? It's like, come on. That's really slow here. Must be the Wi-Fi, I guess. Project? Okay, it's not going to let me do that at all, is it? Well, that didn't work out. Okay, well, I'll just have to do it locally then.
Sad.
Yeah, I think it must be the Wi-Fi or something, because it worked fine in my office. I tried this in my office, and it was, oh, there we go. Now it's coming up. Come on. Yeah, it's just too laggy. All right, it's fine. All right, so have to wait for the VM to open it. not a big deal. Try that one more time now that I'm plugged in. Nope, okay. All right, so now if we go to Files, open up neosystem.qsys, that'll bring up Platform Designer. So what I want to show you is a quick demo on how you can add a SystemVerilog based component to Platform Designer. And then you can then obviously write software that runs on the Neos processor that interacts with it. So you can, when we do this, this is like the purest form of hardware-software design because we're doing the hardware and the software design together. So once this comes up,
So wait, are you saying you're going to write Verilog components manually and then import them into QSys?
right?
Okay.
Yeah, yeah. It's actually
Interesting.
easier than you might think. Now the one thing though, the only thing you have to know is, you know, in QSys or QSys as a platform designer, all the component or mostly the components in there communicate through Avalon, right? So there's another bus that you will have to cover here real quickly. It's not too complicated though, believe it or not. It's actually a lot simpler. If you ever heard of AXI, that's the one that ARM has, like the one that's on your phone. AXI is a lot more complex than Avalon. Avalon's a very simple protocol. It's the one that, actually I think you have the option of AXI or Avalon. We're using an Avalon bus. It's the on-chip bus that's used in SOPC Builder, sorry, they keep changing the name. It used to be called SOPC Builder, then it was QSys, now it's Platform Designer, but the platform tool that we use. Can I download this and open it? And that's not what I meant, buddy. Oh, show in folder. Nope. Okay. Come on, buddy. All right, never mind. Okay, so Avalon bus is a master-slave bus, much like SPI. The main difference, and it's also synchronous. There's two differences, though. One is that the Avalon bus is parallel. It's a parallel bus. It's not serial. So the data channel has multiple, it sends words at a time. The words can be 8 bits, 32 bits, 64 bits. I think it goes all the way up to 512 bits or 1024 bits. It's up to you. But it's a parallel bus. The other difference is that it uses this thing called a bus module. So the Neo CPU is a master, has a master channel. Actually, has two masters, one for data, one for instructions. And then you have these peripherals, and we're going to create a custom peripheral that'll have a slave interface. And so the Neo CPU will communicate through its data master, and it'll communicate with the slave port that we're going to add. But it goes through this Avalon bus module, which means that they're not directly connected. So the pins that come out of the master do not necessarily match up exactly to the pins that are on the slave, because the bus module is a middleman that sits in between. Now there is a lot of commonality though. So here's another picture of that. So you've got the Neo CPU, and then you've got like another module that can be has master ports, so write master and read master. That's on a DMA controller. We're not going to use that in this class, but we do in 313 though use a DMA controller for the video. But these guys are masters, and then you've got slaves over here, and you can see that some of the connections kind of feed straight through to the slaves, but then there's other ones that get kind of intercepted by logic inside the bus module and then get converted to other stuff on the other side. So I have a table. Yeah, so the master interface is here. Now, you don't have to use all these signals. Some of them are optional. So there's a clock and a reset because it's a synchronous bus. There's an address that can be 1 to 32 bits. Byte enable. You can have a byte enable that allows you to like enable, like if you have a 32 bits but you only want to use 8 bits, which is one of the bytes in the 4 bytes available. That byte enables use to control that. That's optional. Read is that basically tells you want to read. Read data is the data you want to read. This says 8, 16, and 32. I thought you can go beyond 32 bits, but maybe Avalon is limited to 32. I know AXI you can go beyond 32 bits for the data. Write is a control signal that says you want to write. Write data is the data you want to write. Wait request is coming back. That is what the slave says he wants you to wait. Then the IRQ. So check this out. The IRQ is part of the Avalon bus. So if you have an interrupt coming from a peripheral, it's actually conveyed through the Avalon bus. I've never actually used that in Avalon before. And then there's an end of packet. I've never used that one. It's optional. Read data valid is the way the slave says the data is valid. And then flush, I don't know exactly what that does, but that's an optional one. It's also one that's on the master interface, but not on the slave interface. The slave interface has chip select, begin, transfer, and byte enable that are not on the master. So these are signals that are being sent from that are being generated from the bus module. But then you've got clock, reset, read data, write data, and so forth. So you gotta. Most of these are optional. But so, and I'll show you how you set those up here in just a minute. So here's an example. So here's the master, here's the slave, bus modules in between. The master has address, data, and control. And then on the slave side, you've got clock, address, byte enable, read, chip select, and read data. And so the way it works is that on the master, you say, I want to do a read, you send the address, and then in the next cycle, it's expected that the slave will send the read data back, right? And yeah, that's basically it. It's pretty simple. It's as simple as I can get. It gets a little bit more complicated if you want to allow the slave to tell the master to hold, to wait. There's a wait signal that you can send, like right here. So here's an example of that, where if the master requests a read, the slave can say wait request. It can hold that high, so it can drag out the transaction. And this makes sense. Like for example, consider the case where you have an SPI bridge, right? The master is going to tell the SPI bridge to send something or to read something, and the SPI bridge is going to be slow because it's a bit serial. So it's going to have to tell the master to hold while it does the SPI transaction and then sends the result back. So that's but we're not going to use that. That's a little bit more complex. So I'll come back to this, but let's just give you an idea of how Avalon works. So if we go back over here to Platform Designer, there it is. You can create a new component just by double-clicking on New Component. And you give it a name. I'm going to call it LED Controller. And there's a name and a display name. I usually just set them the same. Then if you go over here there's some tabs here. Usually after I type in the name, I hit finish and save it. And then I go back in and edit it, because if you don't do that, when you create the files for it, it's going to name a new component instead of the name that you gave it. But now that I have it saved as LED control, there's probably actually, it probably could have just went file save here instead of closing and reopening. But the point is that you want to save that. And then if you go to signals and interfaces, you can add your interface. So the first thing you want to add is your clock input. And the one thing that's a little strange about this is you add the clock, but that's just adding the notion that there's a clock. To add the physical clock signals, you have to actually add a signal under that. So it's a little redundant, but you add a signal, I'll call it clock. Okay, and then I'm going to add another interface, which will be a reset. And I'll add a signal that'll be called reset. And then I'm going to add an interface, and this is where I'm going to add the Avalon memory mapped slave. So it turns out with Avalon and AXI, the master and slave is just the interface type, right? So you can have one peripheral that might have 3 slave interfaces and 10 master interfaces. It's a quality of the interface. So I'm going to add in this case, a memory map slave interface, and then under that I have to add signals. Now this is where the optional signals come into play. You get to pick which signals you want to use as part of the Avalon interface. You have to I think there is some minimal set though. So we want to add address, and we want to add, I want to make this a write only. I want to assume that I'm only going to write to this thing, not read. So I'm going to add write data, and I'm going to add write. Write is just the control signal. And I think that's it. I think that's all I need. And then for address, I'm going to pick 10 bits. And for the write width, I'm going to say 32 bits. Oh, sorry, 1 bit for write. For the write data, I'm going to make that 32 bits. Okay, and then if you go back up to Avalon slave, you have to pick the associated clock and associated reset. So I'm going to use clock sync and reset sync, which are the two clock and reset I added earlier. And that's it. That's all you got to do. And then if you scroll over to here, it'll actually show you a timing diagram of how how it works. It's a little cut off here. Let me maximize. No. Here we go. Yeah, so you can see this is the timing diagram, right? So basically all you have to do is raise write and give it an address and a data for 1 cycle. That's all. Now that's what it's going to look like from the master and the slave side. The master side is going to be generated from the neos. So we don't control that, but this is what we have to expect to see on our side, on the slave side in the Verilog that we're going to write. Okay. Now the problem is that what am I going to do with this peripheral? I want it to control the LEDs, so I have to add a conduit that'll give me an external connection to the LEDs. So I'm going to add an interface called conduit. That's just like a direct output, and I'm going to call it LEDs. And I'm going to say, yeah, that's it. And then, of course, you have to add the signal under there. Come on, buddy. And the signal is going to be called LEDs as well. And it's going to be 26 bits. So this is kind of like the, and I'm going to hit finish, save. This is kind of like the programmed I/O that I showed you earlier. The programmed I/O, though, is where the CPU would directly write to the LEDs. In this case, I'm going to have a little module that's going to do the work. Let's see. Am I out of time? 3:25. Yeah, no, I got 10 minutes, right? Okay. Good. All right, so I've got that created, and if you double-click on that LED controller, it's going to add it to my design. Just hit finish, and then you just have to connect this stuff up. So for clock, I want to connect it to the same clock that, say, the CPU uses. So I'm just going to click the CPU clock. It highlights the clock signal there. I'm going to trace it down and connect it right there, right? Yeah. Sys clock, right? If you hover over that bubble, this is so confusing, but it says sys SDRAM PLL 0 sys clock. So this is the system clock that comes out of the phase lock loop. Okay? So this is the main clock, basically. We have the clock 50 that comes in. It gets used as a reference clock to generate the sys clock and the SDRAM clock, and we want to use the sys clock for this. And then for the reset, I'm going to click reset. I think all the resets are common, so I'm just going to use that reset. And then for the Avalon slave, that's going to connect to, I got two options here. The Neos has a data master and a instruction master. I want to use the data master because the instruction master is only going to be used for reading instructions. The data master is going to be used for I/O, right? So data master. And then the LEDs is a conduit, so I just double click the conduit thing and I'm just going to name it LEDs. And that's it. I should be good to go there. LED controller. Okay, so it says it needs an associated reset. So I'm going to go back to edit on that. And I go back to signals and interfaces, connect the slave, change the reset. Okay, now while I'm in here, there's one additional thing I got to do. I got to go into files, and I got to say create synthesis file from signals. And it's going to generate a wrapper for me that I can fill in to put my code. This is what I was talking about. You see how it says wire here and not logic? they don't give you the option to do SystemVerilog. You only get Verilog or VHDL. So I'm going to pick Verilog. Just be aware of the wire versus reg thing. Okay, then you just hit save on there, and then you just hit finish. Let me double check one more time that reset sync is set. Hit finish, save, and hopefully that will clear up the errors there. There it goes. Come on. So this is another problem. This is an issue with using the SSH file system, because every time it writes files, it has to send them to the lab machine. Okay, so now I'm getting an error about the data master overlapping the whatever. That's fixed just by going to assign base addresses under system. So I'll have it automatically assign the addresses. Okay, we're good to go. So I'm going to just hit generate HDL and generate. And that should generate everything. I think that's the save. Yeah. Okay, now while that's doing that, if we go back to Quartus, this is, it's the local one. If you go to File Open, you'll notice that the LED controller.v is now in, it's actually put it in the root directory of the project, right alongside, lights.sv. Now, obviously, I'm going to be mixing Verilog and SystemVerilog together now in one project. That's okay. And of course, the Neo System QSys is in there too. So if I double-click on LED controller, I can see this is the wrapper. So this gives me my module line, which is everything it needs for the Avalon bus. All you have to do is talk to these Avalon signals, and you can participate in the slave side of the Avalon transaction. So the way I'll handle this is I'm just going to type always at pause edge, and then I'm going to double click this clock. It's got a weird name, clock sync, whatever, but that's the clock, and then begin, end, and then I'll just say if the write signal, which is called write, Avalon slave write, if that's asserted, then I am going to set LEDs, and I'm going to use the address, Avalon slave address, as the actual address to the LED, which will be 0 to 25, because there's 26 of these LEDs. And then I'll set that equal to the same thing, but I'm going to complement it. So I'm going to put a tilde. So basically what this will do is I am going to send an address. I'm going to do a write. I'm going to send the address. The data doesn't matter. I'm going to ignore the data, because there is write data. But I'm actually going to ignore the write data for now. I'm just going to say if you write, regardless of what data you write, I'm going to take the address of the write, and I'm going to use that to index into the LEDs, and I'm going to toggle that LED. Right? Now the address doesn't include the base address of the peripheral. So the peripheral will have a base address. That will get subtracted out before you get this address. So if this has a base address of, say, 1000 in hex, and I send 1004, it'll actually just see 4. And actually, it won't even see 4. It's going to actually see 1, because if I kind of went past it fast, but in the configuration screen, it said that the addressing should be words. So whatever address I add to the base address in the Neos processor, that address, well, first it'll be, obviously it takes the base address out, and then it divides the difference by 4. And that's what I'll get in here. So again, if this has a base address of 1000 and I write to 1004, this address will be a 1. You can change that, though, by the way. That's a setting. But that's something that's handled by that bus module I was telling you about, that bus module that sits in between the Neos processor and this thing. That bus module is what actually does that divide by 4 operation on the address. So it gets in between. Okay, so now my module is done. Now, one other thing, too, this is one thing that's really annoying about this. If there's an error in this file, and it compiles, and it gives you an error in Quartus, if you double-click the error, it'll open the file. Don't edit that file, because this file, which is in the root directory, home, CSCE, 611, lab machine, lights, This file is in the root directory. This is an upstream file. When you generate the system in SOPC Builder, it's going to copy this and put a copy of it in the generated code, right? If you change the copied version, it won't take effect, right? You have to change the original, okay? So I'll show you what I mean by that, because I'm sure there's an error in here. There always is. So now I've saved that. I guess that means I also have to regenerate the code too in S Platform Designer, don't I? Yeah. I think I do.
I could just be safe.
Yeah.
I hate when I forget to update platform.
Well, it's actually it's generating now, so yeah, that's good. All right, so that's pretty much it. So I should be able to, once that generates, I still have to compile it. Is there any way I can get that other Quartus to work? I'd really like if I could.
You call that work?
Let me try another machine here. How about L-3D22-02?
The whole time I've been here, I've never used the name of the lab machine. I've always just been using their IP address.
Oh, sorry. Yeah. Yeah, that's the 129, 252, 130, 101, 102, 103. Okay, get Duo. Okay, so this is 02. Now start up Quartus on here. See if that's any faster. Oh, it seems a little faster. Okay. Now also, you can tell, it's not really obvious, but if you look at here, you can see that this one's running on 02. So if you ever do this, you got Quartus running on multiple machines, make sure you double check the top just so you know which one you're using. So if I, let's see, can I open? No, why? Wow, it's crazy slow here. Okay, that's fine. Let's go back to here. All right, so this is the one that's on the local one. I think we're good to go. So I'm just going to go ahead and compile. And I assume Platform Designer finished, right? Yep. Yep. And Quartus. Yeah. Oh, I should have did Open Project. Do you see how slow the menu finally popped up? Yeah, that's too slow to use, though. Okay, so once this gets done, I probably won't have time now. I probably won't have time to get this done because it's 2:35 or 3:35. I'll finish this in lab on Wednesday because I got to give a lecture on the next lab in there anyway. But what I was going to do is once this compiles, I was going to deploy it to the FPGA, and then I was going to do the thing where I connect through the debugger and just write directly to that peripheral, and then you can see, the lights will come on depending on what address you write. Yeah, that's it. So in the next lab, you'll just create a LED controller, but that one's going to generate a PWM signal. So you're going to take the code you guys wrote the PWM in bitbang form on the software-driven PWM. We're going to do a Verilog version of that, which is a more natural way to do it. And then the advantage is, you might say, well, why would we do it in Verilog? We got it working in software. What's the big deal? Well, this way, we're going to actually independently control all of the 26 LEDs, all independently, because in the software version, you guys had them all getting dimmer and brighter all together, like they were synced up. We want to independently control all 26 of them, and then we also will control the fading out part will be done through hardware. So we'll control the PWM signal and the fading out, and then the software will still be involved. The software, we're going to use the software to generate random numbers to have them random ones come on bright and then dim, right? And so there's actually a video of that. If you look at the lab sheet, I've got a link to a little video on YouTube that shows you what it's going to look like. It looks kind of cool. It's just lights coming on and then dimming out randomly. Okay? Okay, we'll see you in lab on Wednesday.